Cobots, or collaborative robots, came about from the need for more ergonomic ways to do manufacturing, driven in part by new OSHA standards for working conditions. The first ones were introduced in 2008 by Universal Robots, and many factories and manufacturing facilities today are using them. They can be used in almost every step of the manufacturing process and can work alongside human workers to make their jobs easier. The assets they bring to a company include a decrease in human error and injuries, as well as consistency in production time. There are some downsides to cobot use in manufacturing. These include the need to take more time to train the employees on interacting with the robots, and potentially downsizing the workforce due to not needing humans to do the jobs the cobots are now doing. We chose this topic because some of us have worked in automation, and we are all interested in robot use in manufacturing settings. Automation and robotics seems to be the future of manufacturing, so it is important to be aware of the impacts of cobots on the future of the engineering field.
Lean is an important concept for developing efficiency in modern-day manufacturing via the identification and mitigation of waste in the manufacturing process. There are 3 different waste categories in lean manufacturing: Muda, Mura, and Muri. Muda is processes that use resources while not benefiting the consumer, such as transporting products after production. Mura is any uneven workflow issues in the production of a product that is due to inefficient production planning. And finally, Muri is overburdening of production equipment or operators during the manufacturing process. In Lean, all of these wastes need to be mitigated in order to maximize customer value or the overall worth of your product for a consumer. It is a difficult process trying to maximize production efficiency for a manufactured product. This is especially true if some processes that are conducted simply do not have a more efficient system created yet. But the benefits of analyzing manufacturing system for waste not only leads to the easier creation of a good, but also more profit margins and happier consumers. That is why lean manufacturing and its subsets can and should be applied to any manufacturing system to assure that these benefits can be maximized.
Value stream mapping is a lean manufacturing process that follows the flow of materials and information throughout the entire process, from procurement to production to shipment out as a final product. You can see in this visual here what a value stream map looks like, and how the information and materials flow through from the supplier, through the manufacturing process, finally to the customer. Value stream mapping utilizes a principle known as takt time to optimize efficiency based on customer demand of a product. We chose to discuss this topic as it is an optimization technique that looks at the production process holistically in a unique way to increase overall efficiency. This is a technique that we have not seen used before. Value stream mapping can identify areas of waste and reduce the time spent on each stage of the process. Some limitations, though, are that it is simplified and may not show the whole picture of more complex processes. Also, it requires a great deal of information sharing between departments that not all facilities are equipped to handle. By using value stream mapping in conjunction with the 6 lean principles listed here, it can be a powerful tool in manufacturing processes.
This special topic that I'll be discussing is the Kano model, and so this is a Japanese framework originated by researcher Noriaki Kano in the 1980s, and its purpose is to map customer satisfaction and needs met in the product development process. My team is interested in this because it's based off user-based design, so it's designing based off the needs and wants of the customer. Its capabilities include that it can improve customer satisfaction, differentiate a product from its competitors by identifying needs correctly, and helps designers prioritize features to improve or add when creating a product. Its limitations include that the Kano model doesn't take manufacturing processes into account because it's very design heavy. And this can improve design and manufacturing processes because it structures product design to center around identifying different levels of consumer needs, and it helps to promote iterative design processes. So the process can be shown on the right. So it starts with identifying user wants and needs, and then using those different needs to categorize product features, and then from there prioritizing product development based off ideal features, and then monitoring and improving the product. This next slide is just showing the Kano model breakdown. So the x-axis shows achievement, the y-axis shows customer satisfaction, and the bottom arrow is the expected needs. So these are must-level qualities that the product must have. And then the next line is normal needs. So it includes all the must-level qualities, but also a few consumer wants. And then exciting needs include the wow factor qualities in a product that makes it stand out versus other products in the other competing products. The next topic we'll be discussing is digital twinning. Digital twinning is an iterative digital representation of a physical process that evolves as the process develops. And this process is that a digital model is created of a machine or component, and then that machine or component is manufactured based off of that original model. Once the product is used, the ultimate component changes, and so reverse engineering is used to model the modified product, and so this keeps happening through a product or component's life cycle, and so you can track the changes in a product as it's being used. The types of digital twinning include component twins, which is digital twinning of a product or machine, and multiple component twins become asset twins, multiple asset twins become system twins, and multiple system twins become process twins. Applicable industries where this is found is power generation equipment, manufacturing operations, the automotive industry, and healthcare services. Our team is interested in digital twinning because its frequent updates can track the status of a product and predict failure, which is an interesting approach to troubleshooting. It's a part of Industry 4.0, which is ultimately an interesting direction that manufacturing is going in. A couple capabilities include that it improves manufacturing efficiency, improves R&D, helps manufacturers determine end-of-life processes. A couple limitations include cost, complex processes for unique requirements, so it's hard to use in niche situations, and poor data quality limits digital twinning capabilities. This can improve design and manufacturing methods because it can make a product's manufacturing process more efficient with past data and has the capability to be scaled to a factory level.
Throughout manufacturing history, there have been 4 main industrial revolutions. This timeline shows when they occurred and what they entailed. The first one, beginning in 1765, brought the use of steam to power processes, like the steam engine. Next was the introduction of electricity in widespread use in 1870, along with the combustion engine and gas and oil for power. The third revolution began in 1969 with the first uses of automation in computers and processes. That brings us to the topic at hand today, Industry 4.0, or the introduction of intelligent computers in manufacturing processes. With the pace new technology is introduced today, manufacturing has been on a fast track to increase the use of automation and robotic systems in plants. Industry 4.0 capitalizes on these new advancements, and we expect them to capitalize soon on the growing use of AI, as we'll discuss later in this presentation. Pros of integrating the new technology from Industry 4.0 include increased productivity on plant floors, as new technology is faster than human hands and older technology, and optimization of already implemented processes. On the other hand, implementing this new technology will make some currently used tech obsolete, which means it will have to be thrown out even if it is still working fine. We chose to discuss this topic because we believe this technology will change the face of manufacturing as we are entering our careers.
Retrofitting is a very exciting way to connect older manufacturing processes to Industry 4.0. Retrofitting is the process of modifying older manufacturing machines so that they have an increased automation ability. This ensures that machines deemed obsolete in the modern manufacturing age can be used with the same benefits as machined parts until a better, more interconnected manufacturing system is created. Retrofitting can be applied to any manufacturing process that requires machinery, though is especially valuable for processes that currently take a long time for production, but need to be faster as efficiency increases when retrofitting occurs. Of course, this process cannot be done by every manufacturer as it can be really expensive and time-intensive. The entirety of the manufacturing process has to be investigated to ensure that the retrofitted system is applied well, and new jobs have to be made for installation and ensuring that the system runs smoothly. If a company is willing to invest that time and money, however, retrofitting is a great way to take their manufacturing process into the future with Industry 4.0.
A lights-out factory, or a dark factory, true to its name, is a factory that could operate with the lights out, i.e. with no hands-on human labor required. Using advanced manufacturing techniques like cobots and artificial intelligence, these facilities can reduce human error in production and boost overall efficiency. In addition to increased efficiency, companies can save money on the workforce as they do not need to hire as many workers for the plant floor. The risk for injury to an employee is also greatly decreased as fewer people are interacting directly with operations and for fewer amounts of time than in a traditional manufacturing facility. There are some potential cons to this type of manufacturing, however. If a part of the process errors or goes down, the downtime caused by this will be greater than if it were just a human error. The engineer will have to be called to come fix it, and that could cause entire parts of production to be stalled. It's also an expensive technique as new technology must be implemented in all stages of the process. Many manufacturing facilities are implementing partial lights-out practices using automated systems and technologies while still having humans as part of the process. We expect that more and more manufacturing facilities will be shifting to this type of manufacturing. We chose to discuss this topic as it had never occurred to us that a factory could operate completely without human interaction. We are interested to see how it plays out in the future.
The next topic we will be discussing is augmented reality in manufacturing. So a summary of this is that AR manufacturing integrates digital technologies into production operation and allows workers to interact with digital components as if they were real. We're interested in this special topic because it's innovative and exciting technology integrated into manufacturing, and I can see this becoming a very wide-scale process used as this technology develops. A couple capabilities of augmented reality in manufacturing is that it helps companies improve productivity, reduce operational costs, and optimize workflows, and it can allow manufacturers to detect faults, optimize workflow procedures, and improve maintenance operations. And so this can be helpful with troubleshooting and improving manufacturing processes. Couple limitations of this is if there are technical difficulties with the AR interface, the display can cause safety risks for manufacturers. So this technology can ultimately influence the safety of workers, which is a negative, but it is something that as the technology improves, this can be mitigated on a large scale. And this can improve design manufacturing methods because utilizing AR into manufacturing improves ergonomics through improving accessibility, so it can be fine-tuned for different workers, and it can be used to improve troubleshooting efforts.
An important aspect of design is ensuring that products being designed will not fail. That is why design for reliability is so important. Design for reliability is the process of verifying that a product will last for a desired amount of time and ensuring that any potential faults or failures are accounted for. There are two primary methods for design for reliability. First is failure mode and effect analysis, or FMEA. FMEA is pinpointing any potential reason for an object to fail, understanding its effect on the object as a whole, and planning methods to mitigate the failure's probability. Then there is fault tree analysis, or FTA. FTA is the opposite of FMEA in that you look at a failure in a system and trickle down until you find the most probable cause via the use of logic trees. Both methods are valuable in the design of a new product because they are systematic in the analysis of failure points. Instead of blindly going through the design process, FMEA and FTA force the designer to look at every avenue for failure closely and ensure that it is not an issue. That is why these methods can and should be used on any sort of design and manufacturing process, as they can be related to any issue that occurs from faults and failures. While one can argue that this process is long and arduous, the benefits of this systematic design method cannot be overstated in assuring that a product has a long and successful lifetime.